Good morning, students. Today, our topic of discussion is construction of H matrix, encoder, and decoder circuits for linear block code. Error correcting codes are mostly utilized in communication and storage systems for detecting as well as for correcting errors. At the transmitter end, the encoder circuit of any ACC scheme generates the code word to be transmitted. And at the receiver side, the decoder circuit of ACC, it detects and corrects error caused by the transmission channel or maybe for in any storage medium. An NK linear block code takes k bit data as input and provide n bit data as output. So this n bit data is called the code word of the code. And NK linear block code is completely characterized by its H matrix. Now H matrix basically it having dimension n by k by n, that is n minus k rows and n columns. So among n columns there are n minus k parity columns and k data columns. So parity columns in the H matrix are generally created by applying identity matrix of dimension n minus k by n minus k on the left side of H matrix, as well as the data columns are k number of data columns are there and which are on the right side of the H matrix. Now column selection rule for H matrix. Now before constructing the H matrix, we have to set the rule for selecting the data column, because parity columns, as we know, it is very easy to generate. Simply identity matrix will be using to uh, generate the parity columns. Now, so to set the rule, we need to know what kind of code or the H matrix for which code we are looking for. So if we consider single error correcting code, that means these codes are capable of correcting only one error inside a code word. So this code, single error correcting codes or ACC, in that case, the column selection rule is very simple. Simply, all the columns in the H matrix must be non-zero and distinct. So there must not be any all-zero column in the H matrix, as well as each column must be different from one another. Now, if we are considering double error correcting code, so in that case, all the columns in the H matrix must be non-zero and distinct. So this is the same as uh, the column selection rule for ACC code. That means to design DEC code, that is double error correcting code, we have to obey the ACC rules as well as the DEC. So the rule for DEC is that all the actual sum of any two combination of column in the H matrix must be non-zero, distinct and different from any column in the H matrix. So here the illustration has been shown for the H matrix. So first we have parity column. So P1, P2, P3, P4, because we are considering now 8-4 linear block code or 8-4 LBC. So 4 parity column as well as 4 data columns. So parity columns we have indicated by P1, P2, P3, P4, and data column has been indicated by D1, D3, D2, D3, D4. So for parity column in the lower matrix, as you can see, for parity column we have simply used the identity matrix, 4 by 4 identity matrix, and for data column we have used non-zero and different combination of 4 bits, any 4 bits, any 4 combinations. Now once the age matrix is constructed based on some uh, design rule, so first task is that we have to uh, convert the message bit to the code words, and that is done by the encoder circuit for any linear block code. So 8-4 encoder circuit, for 8-4 linear block code, the encoder circuit. Now let us see how to design the encoder circuit. So same age matrix has been shown in the right side. Now parity column is P1. So P1 means, as we can see that uh, at the first row we have 1. So we will traverse the first row, we will be checking for 1, and we are going to exert the corresponding data position. So here 1 is at D1, so D1 XOR D3. So the expression for first parity column or first parity bit is P1 equals to D1 plus D3, or D1 XOR D3. So similarly, other parity columns expression also we can determine from the same H matrix. So from the same H matrix, P2 is D2 plus D4, because we have in the second row, if we check the second row of the H matrix, so D2, what is the column D2? So D2 column, below that in the second row there is a 1, and D4 there is a 1. That's why D2 XOR D4. So once these expression of parity bits are obtained, in the simple way we can design the encoder circuit by taking only the XOR gates. So only XOR gates, and we are going to XOR the data bits as per the parity equations. So the encoder circuit for 8-4 linear block code we have shown here on the left side. So based on this, so first parity expression is D1, D3. So data bit we have taken as input to the encoder circuit, and D1 and D3 we have taken here for the first parity bit. So once these parity bits are generated, the encoder also combines these parity bits as well as the data bits to form the code word, and these code words are transmitted over the noisy channel. Now decoder circuit. So encoder generates the code words. So this code words has been indicated here by V, and this is transmitted over the channel. Now in the channel there is a noise, so error will be caused, and this error has been indicated by E. So this error is added to produce the received code word. So R is basically XOR of the transmitted code word and the error pattern E. Now at the receiver side, the decoder has 3 major functional blocks. The first block is called syndrome computation. Next we have error location detection, and finally error correction. And after error correction, we will be getting the corrected data bits. So first step, syndrome computation. So to compute syndrome, so first of all, we need to obtain the expression for syndrome. And once again, the syndrome expression we can obtain from this H matrix itself. So here, uh, the same 8 matrix of 8-4 linear block code has been reproduced, and we can see we have marked is as row wise R1, column wise R1, R2, R3, R4, R8. So R stands for received code word. Now at row we have indicated like that S1, S2. S1 means first syndrome bit, S2 means second syndrome bit, so on. Now just like the encoder circuit, so to determine the expression for H1, once again we will be traversing through the row of the H matrix. So for S1, this is the first row. So first row There is a 1. What is the corresponding receipt code word position? R1. So R1 XOR, here there is a 1. R5 XOR R7. So this is the expression for first syndrome bit. So similarly, for second syndrome bit, we will be traversing the second row of H matrix and corresponding values of uh, receipt vector bits will be XOR. So once we get the syndrome expression, so syndrome circuit once again just like encoder circuit simply XOR, nothing else. So receipt vector R1 to R8 are taken as input, and these input are XORed as per the syndrome expression to get the syndrome bits S1, S2 up to S4. So this is the second step, syndrome computation. Now third step is the error location detection. Now error location detection once again uh, we can do once again by inspecting the H matrix itself, nothing else. So for first data position, so basically one more thing, that only error correction is performed on data bits because all the important messages are carried by the data bits, and parity bits are added to the data bits as to form the code words so that it can detect as well as can correct errors if it is caused by the transmission channel or maybe in storage medium. So to detect the error, first of all at D1, so D1, for D1, so if the syndrome value matches with the column corresponding to D1, that is 1010, then only we can say there is an error at D1, otherwise not. And once again we are dealing with single error correcting codes. So corresponding syndrome value 1 means S1, at the left side S1, 0 means S2 bar, S2 complement. Now once again 1 means S3 and S4 means S4 complement or S4 bar. So for the first data bit LDD1, the expression is only by checking that particular column and corresponding writing the corresponding logical expression in terms of syndrome bits. So syndrome bits S1 and S2 bar and S3 and S4 bar. So similarly we can construct or we can write down the ELD expression for each and every data bit in a particular code. And this is written here. We have 4 data bits. That's why I have written 4 expression here. Now these expressions once again we can represent in logic diagram by simply considering what we have in the expression. We have and as well as not. That means by simply using and as well as not logic gates, we can express logically these expressions. So that is done here. So here input is the syndrome bit for LD circuit and output is the LD expression for each and every data bit. And one more thing, LD circuit output 1 means error is located at that data position and that must be corrected, and that correction is done by error correction circuit. So error correction circuit means simply we need to flip the bit in error. So bit flipping is generally performed by using XOR gate, and XOR gate what we have, LD circuit input as one input and corresponding data position or corresponding receipt vector as another input, and output is the corrected data. Okay, so simply by using XOR gate we can correct the error. So this is the scenario when we have combined all the 3 component of encoder circuit for linear block code. So first of all we have syndrome computation block. This is the first one, the first block, syndrome computation. Then we have error location detection, middle block, and finally the error correction block, which is nothing but a series of XOR gates. And ultimately, we are getting the corrected data. I hope this lecture will be helpful to you. Thank you.